Example 9.3.2. Calculate the IRR, or internal rate of return, of a one-year project. All right, and this setup is going to look familiar because it's the same setup from 9.3.1 where we calculated the NPV. It says your firm has the opportunity to invest in a project that will cost $500 today and yield $550 in 1 year. You estimate the project's risk-adjusted weighted average cost of capital at 6%. Your firm can also borrow and lend at 6%. What is the project's IRR, and should your firm invest in it? And that should say, of course, according to the IRR investment rule. Okay, now we're using the same setup so that we can explore the relationship between NPV and IRR. And IRR goes by at least three different equivalent definitions that we'll take advantage of to be able to calculate it and interpret it. So the first definition is that the IRR is the discount rate at which net present value equals 0. So in other words, we would set up the same net present value equation, and we would set that thing equal to 0, and we would solve for the rate that makes it true, which we'll do in just a minute. Another definition is that IRR is the discount rate that equates the present value of the benefits with the present value of the costs. And those two definitions turn out to be equivalent, the first one and the second one. Because when NPV is equal to 0, then it must also be true that the present value of the benefits are equal to the present value of the costs. So those are really just two different ways of stating the same thing. And then finally, and this final definition is how we use it as an investment decision rule to decide if we actually want to take a project on or not. And that is IRR is the project's rate of return if all cash inflows are reinvested at the internal rate of return. And that should really be a big if, because that turns out to be a big limitation of the internal rate of return. And we'll see when we set this up why that's true, although with one cash flow here, it may not be quite as obvious as it would be with multiple cash flows. All right, and then finally, we know how to set up and calculate the IRR. Then the IRR decision rule to decide if we want to invest in this particular project or not is if the internal rate of return is greater than the cost of capital, then we accept the project. And if the internal rate of return is less than the cost of capital, then we reject the project. Right? And this is relying on that third definition, where IRR is the project's rate of return. So in this example, we've got a weighted average cost of capital of 6%. If we were to find an IRR of, say, 10%, that would mean that our cost of capital is 6%, so it's costing us 6% to use the money and invest in this project, but the project is expected to yield a return of 10%, and so it's returning more than what it's costing us to use the money, and it should then be a positive net present value project and one we would want to accept. So let's set this one up and see how to mechanically calculate the IRR. It's the exact same project as the previous example, where we have a cash outflow today of $500 and then an expected cash inflow 1 year from today of $550. And what we want to do is find the rate that equates these two values. All right, where we've got the cost. Remember, we want to equate the present value of the cost with the present value of the benefits. Well, the costs are already in present value terms. The benefits we need to discount back to time period $0. All right, so if we're going to set this up with an equation, which we can do when there's just one time period like this, we'd set up the NPV definition and say NPV equals the present value of the benefits minus the present value of the costs. And we're going to set this thing equal to 0. So NPV is 0. Present value of the benefits, well, that's $550. Discounted back one time period to get it in time period $0. So we're going to divide that by 1 plus R raised to the 1. That'll give us the present value of the benefits. Subtract from that the present value of the costs. With those are already in time period $0, so no adjustment needed. And then we can just play a little bit of algebra games here to solve for this R. Let's start by adding 500 to both sides. So that we have Now 500 is equal to 550 over, I'm just going to say 1 plus r. We can drop that 1 superscript because anything raised to the 1 is just itself. The two 550s cancel out on the right-hand side. All right, now we want to multiply both sides by 1 plus r to get this guy up in the numerator. If I can create a little more room there. Oh, I've used it up, so we'll squish this in a little bit. All right, and those, of course, on the right-hand side are going to cancel out because we've got a 1 plus r in the numerator, 1 plus r in the denominator. So now we have 1 plus r times 500 on the left is equal to 550. All right, then we can divide both sides by 500. So that they cancel out on the left. We're left with 1 plus r is equal to 550 over 500. And then we can just subtract 1 from both sides so that they'll cancel out on the right. And we're finally left with r equals 550 over 500 minus 1. All right, and we can plug that into the calculator. $50, making an extra $50 on initial investment of 500. That's going to be a 10% rate of return. All right, but just so we can see it go, here we'll take the 550 divided by 500. And then, of course, we need to subtract the 1 off. And sure enough, we get that 10% back. All right, so that is our IRR. So our internal rate of return is 10%. Our cost of capital was 6%, right? And so that internal rate of return is greater than the cost of capital. And so this says, the internal rate of return rule says that we would accept this project because it's going to cost us 6% to use the funds, but we're expected to earn a rate of return of 10%, which would then imply that we have a positive net present value project. And in the previous example, we find that to be exactly the case when we looked at this exact same setup. Now, internal rate of return rule has some issues with it. Net present value in the previous example we found out is a direct measure of how much value a project creates, and in fact is equivalent to putting that dollar amount in your pocket today. So net present value rule is reliable. It's a good one to use, although there's some assumptions packed inside of it. One of them being that you're correct about the cost of capital, but remember we're trying to calculate the present value of future expected cash flows. So there could be some riskiness in those cash flows. There could be some risk in your cost of capital, in fact, if you find yourself in a suddenly rising interest rate environment, like we are right now. I'm recording this in November of 2022, and the Federal Reserve is raising interest rates 0.75 of a point pretty regularly at the moment, and interest rates are going up quickly. You, over the life of a project, could find that your borrowing cost increase substantially over the life of it. So net present value isn't perfect either, but internal rate of return has some significant issues. One of them being that because it's reported as a percentage, like we know an IRR is 10% here when we get to the bottom, well, it tells us nothing about the scale of the investment. So if, for example, you're trying to choose between two mutually exclusive projects and you find out that one has an IRR of 10%, one has an IRR of 50%, well, 50% sounds a lot better, but unless you know the initial investment in the project, you don't have anything to gauge that 10% versus 50% with. in terms of what the actual dollar return is going to be. Right? You could be much better off taking the 10% project if it's a significantly larger, safer investment. Right? And one of the other big limitations is that because we're solving for a rate that makes this statement true, right, we're implicitly assuming that we're able to reinvest all cash flows at this rate. Now, for a one-year project, it's not a huge deal. When we start looking at multi-year projects that last 5, 10 plus years, if we get a really large internal rate of return back, we have to remember that baked into that IRR calculation is the assumption that we're actually reinvesting that cash at that internal rate of return. So if we get something back like 25% over a 10-year project, well, it's pretty unlikely that we're turning around and reinvesting those funds at, say, 25%. So we need to take that with a grain of salt and just know that that limitation is there. And there are ways to deal with that too. But in general, what will happen is the internal rate of return and net present value calculations will be used together because they provide a lot more information than either one does by itself. Now, this chart is taken from the text, and what we've got is the net present value of this project that we looked at in the previous example, 9.3.1, and we found that the NPV was $18.87, meaning that if we were to accept the project and invest in it, it is equivalent to putting $18.87 in our pocket today, and we actually showed how we could construct that with our borrowing costs. And then the internal rate of return of 10%, remember that is where the net present value is equal to 0. So with these 2 points, a net present value at a discount rate of 6% of $18.87, we get 1 point here where at 6% our NPV is just under $20. And then we get a second point when we calculate the internal rate of return because we know that 10% is at a net present value of 0. So from that, we can build what we call a net present value profile, where we map out the net present value at a variety of discount rates. Right? And what we get here in this picture is, among other things, we get an idea of our margin of safety in this project. Because remember, anywhere that it's a positive net present value project, so anywhere to the left of 10% where the net present value is greater than 0, then the project is expected to create value over and above what it takes to pay our financial stakeholders. And so we would take the project. Well, let's say we are worried about going into a higher interest rate environment. We can see from this net present value profile that our borrowing cost would have to increase from 6% all the way up to 10% before this project flips to a negative net present value project, and it would be one we would not want to take anymore. So that's a 4% margin of error. So we could be off by as much as 4%, and this still be a project that would be attractive to our owners. Right? So most of the time, these two will be done together. And in fact, you'll usually do something like sensitivity analysis or scenario analysis, where you calculate NPV and IRR over a range of different scenarios, economic environments, all that kind of thing, which is a lot easier to do with a spreadsheet. And then you would take all of that information and select projects that fit the profile that you were looking for. But in general, these two guys are taken together. Now, in the next example, 9.3.3, we will actually look at how to use the cash flow worksheet to solve for net present value and internal rate of return at the same time. I know we went after these by hand, and that's really just so we could see the mechanics of what's going on and understand exactly what net present value and internal rate of return are. And then we'll introduce a little more complex cash flows and figure out how to calculate NPV and IRR with those using the tools that are available to us.